Hello everyone. Good evening. So today will
Good
be
evening, ma'am.
good evening. So we'll be doing week 4 today. I hope many of you have are already familiar of the initial topics. Yes, Kiran, you have anything?
Yeah, ma'am. I'd like to cover three lectures. But have a request, ma'am. If you would like schedule this open session for every Tuesday or Wednesday, it will be helpful.
Tuesday or
Right
Wednesday?
after, yeah, because right after completing 1 week,
Yeah,
we
I
we
understand.
should get some time to
Yeah,
watch lectures.
no, I understand that. So I okay. The problem from our side that is happening is the sessions will clash. Some sessions will clash. So
Uh, is it fine for Tuesday?
I don't know. I mean, I need to check. So, is it the same for everyone? Like all of you would want to move the session of Monday to some other day, or this Monday is fine?
Not really, ma'am. This Monday is good.
No, ma'am. Classes are there, ma'am. Other classes.
Yeah. That's what my concern was. Like some classes will be there. Um,
Yes, ma'am. That's what already the schedule is there. We should not change it. Otherwise, again, we have to manage. Now weekly. We are trying to
yeah,
catch up.
let's stick to the schedule. Yeah, I know.
Ma'am,
Yeah, tell me.
ma'am, today's class is also collapsing with system commands instructor class. So please try to change the schedule.
The commands. Is it okay? So, okay, I think you
All
all
the sessions are in the evening from 6 to 10. So some or the other subject will anyway
will
clash.
always clash. That's yeah, exactly. Some of the session will always clash.
Ma'am, if the TA session is classing, it's okay, but instructor session is classing is like not good for us.
Yeah,
Um,
but they are people with different
like
subjects.
yeah, like all of you have different set of subjects with you, and it's quite tough to come up to a schedule which matches with everyone schedule. So there are not many slots available, or one possibility could be that we can do in the morning, but then morning many of you will not be available. So
It's fine, ma'am. Morning is fine. Or
then
Yeah,
maybe
morning is fine, ma'am.
Then you can do
we
maybe a
just
poll when more students are there, morning or evening, morning or no time change.
ma'am, afternoon also is fine.
yeah, but there are many working
Morning is
professionals who join the session, so it's difficult for them to manage in the afternoon or morning. That was the only reason the sessions has been kept in the evening.
Working professionals.
Um, okay. Can we get a raise of hand who all are okay with this time slot, or like Monday slot? Okay, I don't see 3, 4, 5, 6, 7, 8. Okay. Okay, out of 20 people here, I see 9 are already okay with their schedule. So, all right, let's not change this, I would say, because again, you'll have to manage, you'll have to redefine, recheck your other schedules and so on. Okay, but if I can check, but I'm sure there'll be one or other session on either Tuesday or Wednesday for sure. But okay, let me just check with the team once, and I can let you know maybe in the over the email if it's possible. Okay, because the next session will happen in on Friday now, um, and then next Monday would be Diwali. So yeah, we'll send you an email. Okay, all right. Let's start now. Okay. So in week 4, the topics that we are going to look at is estimation, and another topic is going to be a very important algorithm, which is EM algorithm. So these are the two things that has been done in week 4. So I hope many of you are already aware of the estimation problem.
Yes, ma'am.
Yes. So yeah. So in estimation, one very like what is it? I mean, what is the most important or the most used estimator is? So I mean, estimation problem is the very first is the ML estimation, right? So maximum likelihood estimation. Maximum likelihood estimation. So this is one thing that we'll study, and then there is another part of it, which like other way of estimating the parameters, and that is something which we call it Bayesian estimation, right? So Bayesian estimation is another part. So what happens in the estimation problem? Like you would have like studied this in stats 2 as well. You all have done stats 2 and come to MLB. So you already are aware of many different kind of distributions that are there, right? So let's say you have certain samples. So you have x1, x2, so on till xn, and they are, let's say they are coming from some distribution, right? So let's call the distribution f. Okay, and there is some parameter theta of this distribution. So if you have the samples, I mean the data that you have, prior, posterior. Okay, so the data that you have, I mean, you have observed the data, and what we are saying is there is some underlying probabilistic model that is generating my data set. So the very two important assumptions that we make is one of independence, which and the other is identical distributed, which in short we can write it as IID, right? So IID is basically independent and identically distributed. So this is independent and identically distributed. So these are two assumptions that we make. Now, so what is the goal here? The goal here would be to know what is this theta, right? So what you are observing is just a sample, but there is some probabilistic model that is generating this data set. So let's say if we say, let's say there is some distribution f, and this distribution has this parameter f, a parameter theta. So this theta is what we are calling as parameter, and we want to know the estimate of f. I mean the estimate of theta, the estimate of this parameter, and that we can find, or that we can estimate using the samples that we have at hand, right? So if let's say we are saying that my sample x1, x2, so on till xn, they are IID Bernoulli P. Okay, so all we are saying is that these samples are coming from a Bernoulli distribution. They are IID. So the Bernoulli distribution is something what is generating this data set, and P is the parameter, right? And we don't know what this parameter is. This parameter P is unknown to us. This is not known to us, right? So what we're saying is this P which is unknown to us, but it is a constant, unknown at a constant. So P is an unknown, and it is a constant. Okay. So if we have a setup like this, and we would want to estimate this P, find the estimate of this parameter P, then what we can do is we can use this maximum likelihood estimation. So maximum likelihood estimation, which we can also call it as ML estimation, right? In short, it is also called as ML estimation, ML estimator. So we can use this technique of finding the ML estimate, and we can find the estimate for my unknown parameter P. So what are the steps that we follow while finding these parameter, while finding the estimate for the parameter P? So the very first thing that we do is we write the likelihood function, right? So we find the likelihood function. And how to define this likelihood function? So this is L of P, x1, x2, so on to xn. So we are writing this P because I'm talking about this example over here. Okay, that's why it's P. But in general, if let's say if we have the parameter theta, then I could have written here theta. So we are finding the likelihood function of theta given these samples that we have. So x1 to xn. And how do we find this? We just take the, since all these samples are IID, right? They're all independent. So we can just take their multiplication. We can just do the product of all these. So it will be more like finding the probability or finding the likelihood of P given x1, then x2, and so on, right? So we can write this as a probability. Hold on, I'll come back. So this is like you're taking the product of all these xi that you have, the parameter P, or you can also write as given P, and I is varying from 1 to n. Okay. Yes, anybody had any doubt?
Yeah, ma'am. So likelihood means like conjunction, right? Like all these data point, like probability of all these.
Yeah, probability of all these samples that you have.
Okay, so it's like and, right? And of all.
How? And we are able to do that, and because all these samples are independent.
Okay.
Yeah. So this is how we can do the likelihood, like find the likelihood. Now, what is going to be your, since this particular example is specially for this Bernoulli distribution, can someone tell me what is the, since it's a discrete random variable, what is the PMF of this Bernoulli distribution?
P power k 1 minus p power n minus k.
Yeah, so it is going to be p to the power k 1 minus p to the power 1 minus k. But instead of k, I will just write xi because that is what I have used here. So this is 1 minus xi, right? Where I is varying from 1 to n. Is it clear to everyone why this is the PMF for my Bernoulli distribution? Anyone has any doubt?
Ma'am, intuitively, if we see likelihood should be like a mean of all samples, right?
Mean of all samples.
Or the probabilities of all samples.
Why mean?
Ma'am, intuitively, if we want to like know what if you have to predict something, what will be the average value is the first parameter when it comes to the brain intuitively. Is
Okay,
it
like
somewhere
that.
related?
Okay, like that. Okay, yeah. Yeah, I mean, if I have to think of some metric which is kind of like give a good estimate of the parameter, yeah, then I would say mean is something that comes very first. Okay, so I assume nobody has any issue in understanding the PMF of the Bernoulli. I hope it is clear to everyone.
Can you describe with some example, madam?
Some example. Okay, see, let's say one of the sample. Let's take one sample. Let's take a sample, and since it's Bernoulli, so I would say 1 1 0 1 0. Let's say this is what I observed. Now, what I'm saying is that they're coming from Bernoulli P, right? So P here is what? P here is probability of success, right? And what is the probability that my xi is 1, my x1 is 1, right? This is what I put it. Probability that x1 is 1. And that I will write as P. What is the probability that x2 is 1? That I will write as P again. What is the probability that, I mean, x3 is 0?
1 minus P.
That will be 1 minus P, right? So they are just doing the multiplication of P 1 minus P, depending on whether you have a success or a failure. So it is going to be P times 1 minus P times P times 1 minus P, right? So how many times you have the P? So P to the power the number of successes that you have, right? Since the number of successes here is 3, it is P cubed. So P to the power number of successes and 1 minus P to the power number of failures, right? So this is what we will get. Okay, so let's just put into this. So if xi, xi is going to take, look at this part. So your xi is going to take the value either 0 or 1. Okay, so if xi is equal to 1, it means it's saying success. And if xi is equal to 0, it means I'm saying it's a failure. Right? So if xi is 1, then in that case, I am going to get p to the power 1, right? And what is going to be the other one? So other one is going to be 1 minus p to the power 1 minus 1 to 0. So that would just vanish, correct? So if you just open this and write, you will get p to the power x1, 1 minus p to the power 1 minus x1, right? Then what else do you have? You will repeat this till p to the power x5 times 1 minus p to the power 1 minus x5. Okay. So all these xi's are either 0 or 1. So in case your xi is 1, you will only get the p. And in case your xi is 0, this will vanish and you will get 1 minus p. Okay. This is what we'll get. So you can write your PMF in this way. This is fine. Ganesh Murthy.
Yes.
Please mute
Yes,
yourself.
madam. Yes, madam.
Can you? Okay. So I hope this is clear now. Yes, Kiran.
Ma'am, like, do we need this beta gamma distribution? That's difficult to understand.
Your voice
Are you audible? Okay, just let me check. Yeah, ma'am. Those beta gamma distributions, do we need them for this course?
I mean, see, if we have this Bernoulli distribution, beta will come, right? And for other distribution, I mean, your gamma may also come. So you need to So yes.
Like that is default ones. Can you revise them also?
I can suggest some material. I think in stats 2 this was done. You can go to stats 2 and see once. No, I think gamma, beta, they all has been done in stats 2.
Those two are enough, right?
Yeah, those are enough. Yeah. Okay. So this is how we can write the likelihood function. Now, so what have we done? We have written the likelihood function. So in this case, it's likelihood of P given the samples, which is x1, x2, so on till xn. And this is coming out to be product of P to the power xi, 1 minus P to the power 1 minus xi, where I is varying from 1 to n. Okay. Now, what are we saying? This is just the likelihood function. But we are saying we have to find the maximum likelihood estimator. So we need to find that. So if I have to find the estimator, P hat MLE, it means we need to find the value of P that maximizes this likelihood. Okay. So this is my likelihood. Let's call it LP. What do we want? We want to maximize this, right? So we want to maximize this. And it's not just we want to maximize it. We want to see what is that value of P or what is that value of theta that maximizes this likelihood function. So what we are saying is that we need to know our max of LP, right? And this is what we will do. Only these two steps is what is involved. And we already know how to find this P. What can we do? We find the likelihood. We find its derivative. So we find L dash theta and we set it to 0, right? And once we set it to 0, we can also check for L double dash of theta and see if it is lesser than 0. If it is lesser than 0, we'll know that it is going to give you the maximum value. And after solving this L dash theta, you can get this value of theta that is maximizing your likelihood, and that is going to be your maximum likelihood estimator. So in case of the Bernoulli distribution, the MLE that you get, so if I have to write P hat of ML, it is just going to be the number of successes. So number of successes divided by n. N is the total number of samples. So number of successes, what can you write? You can write this as sum over xi. I is varying from 1 to n divided by n. Okay. And a very, to find this P hat of ML, a very like a popular technique that is used is using the log, not just finding the likelihood, but finding the log likelihood. Okay. So if you have this likelihood and you want to find the log of likelihood, log of LP, what will you do? You will take the log here, right? And when you take the log, the product becomes the summation, right? So you will have log of P to the power xi, 1 minus P to the power 1 minus xi. Okay. So this is just the product. So I can write this as xi log P plus 1 minus xi log 1 minus P, where I is varying from 1 to n. Okay. Now, once we have this, I just have to take the derivative with respect to P. So I will do d of, if I'm calling it as log of LP as maybe small LP, then I will do DLP divided by DP and set it to 0. Right. So when we set this to 0, when you find the derivative of this, what do you get? You get
Sample map.
sum over xi. What is the derivative of log P? It is 1 by P, right? Plus sum over 1 minus xi divided by 1 minus P, and there is going to be minus sign over here, right? And you have to set it to 0. So, or this. So you solve for this, what do you get? You get P 1 minus P. 1 minus P sum over xi minus sum over xi, P 1 minus xi. This is 0. Okay. So what do you have? You have sum over xi minus P sum over xi minus, okay, so you get NP. I think here also you get NP, no? Okay, so this term will basically get cancelled out. This will go away. And what you will have is minus NP is equal to 0. So what do you have to find? You have to find P. So P is equal to sum over xi divided by n. And this is exactly what we have written here. So very simple. I mean, any distribution you have, this is the step. These are the only 2 steps that you do. So you try to first solve without using the log likelihood. If it's a simple problem and if it's doable, then you don't have to go for log likelihood. But many times taking the log and taking the derivative makes it much more easier. So that's why we generally take find the log likelihood and then find the
How this plus sign is changing to minus, madam?
10 into
How the plus sign is changing to minus?
plus sign is turning into minus here because you're taking the derivative of log 1 minus p. So it is going to be 1 by 1 minus p, but you have minus sign over here, so you multiply by minus, right?
Okay. Okay.
Okay. So that's how you can do it. I mean, any ML estimation problem you can do like this. Now, this was about the ML estimator. Now, what about the Bayesian estimator, right? This is something that we want to see. So the second is our Bayesian estimator. So the Bayesian estimate, in the Bayesian estimation, what we have to do is, I mean, what we do is, see, the problem is still the same, that we have some samples that we have observed, and we are, what we want is to find the estimate for the parameter. So it's banally, I want to know what is this theta. I mean, what is the estimate of this parameter? So in the Bayesian setting, what we does is we assume, let's say, this theta, which is unknown to us, but it's no longer a constant. We are saying now it's a random variable. So if we are assuming the parameter to be a random variable, what will happen is that this random variable theta now should follow certain distribution, right? Since this is a random variable, it should follow certain distribution. So we'll start with some assumption or some prior knowledge or some instinct, like, okay, maybe this is what my theta looks like, right? So we'll call this my theta. Let's say it follows a distribution f theta of theta. Okay, this is w theta. So if my theta is a random variable and we're saying it follows a distribution of theta of theta, so this is some assumptions that we're making, some idea that we have about this random about this theta, and this is what we are calling as a prior distribution. So we have some prior knowledge about my parameter, and we are assuming, or we are saying, okay, let's say maybe this is what this theta is following. So that is my prior knowledge. So if this is what theta is following, and after this, once I have the samples, once I see the sample, this x1, x2, so on till xn, if this is the sample that we observed, then after observing the sample, how is your belief changing about this parameter theta, right? So are you still, like, once you have the sample, are you still going to say that the distribution that I thought my theta follows, after observing the sample, is it still the same, or is there something has changed, right? Are there, I mean, are there some other, let's say I thought maybe my theta follows a Bernoulli distribution, Okay, so if my theta follows a Bernoulli distribution with some parameter p, and I have seen the sample, I saw the sample, and based on the sample, now I have to update my belief about this parameter theta, right? So now I need to update my belief about this parameter theta. So what we do is like, what do we want? So we want to find the probability of theta, right? Given that we have seen the sample x1 to xn. So once we have seen the samples, how is the probability of theta? Like, what is the probability of theta now? So why this is called Bayesian estimation? Because if you look at this, it is more like probability of A given B, right? So this is a Bayesian setting where we know if you have, let's say, two events A and B, or right? So we can, or maybe B1, B2, so on to Bn, you can do all that. So how do we write that? So this is more like probability of observing the samples, which is x1, x2, so on to xn, given theta times probability of theta, right, divided by probability of the sample. This is what we will write using the Bayes law, right? So that is one reason we are calling this problem as the Bayesian estimation problem. So now look at this step here, the first part. So this first part, which is probability of x1, x2, so on till xn given theta, is nothing but our likelihood, right? This is my likelihood. So what we have is the likelihood, and probability of theta is what we have as the prior, right? So p theta is nothing but the distribution on theta, and this is what we had assumed on this, what we had started. So likelihood times prior, and the denominator term is nothing but probability of observing the samples, and this is not playing any role on theta, right? This is just probability of this probability of samples. So it is not dependent on theta, so we can just ignore it, treat it as a constant. So what we get is this term that we have, which is probability of theta given the sample, which is x1, x2, so on till xn. So this probability is what we call it as a posterior distribution. Okay, so we are saying this posterior now is proportional to the likelihood times the prior. Okay, so what is the result that we get? We get posterior to be proportional to the likelihood times the prior. Okay, so this is how now let's say if we had started with Bernoulli P, let's say my posterior also we got it as Bernoulli P, but with Bernoulli distribution, but with some different parameter. Okay, so now your update belief about the parameter has changed. Okay, so I mean, it usually does not happen. I mean, if you use Bernoulli as prior, you don't get the Bernoulli as posterior. So I mean, that was just one example that I took to tell you about it. So I mean, you got the idea, right? I mean, if I'm saying my theta is some Bernoulli P, Bernoulli distribution with parameter P, this is my prior belief. But after viewing the sample, let's say my posterior distribution also, I got it as a Bernoulli distribution with some parameter, let's say Q. Then there is some change that has been, I mean, some changes have been done once I have seen the sample. And this is now my updated belief about my parameter theta. Okay. So this usually does not happen. So let me just write here as beta distribution. So let's call that my theta follows a beta distribution. That is, and here theta is nothing but the parameter of the distribution from which my sample has been has come. Okay, so if theta follows a beta distribution with, let's say, parameter AB, okay, then what happens is that my posterior also follows a beta distribution. Okay? So the posterior also follows the beta distribution with some alpha and some beta. So only this has changed. I mean, the parameters of the beta distribution has changed. All right. So such kind of priors are called the conjugate prior. So why they are called conjugators? Like you started with the belief that your parameter follows the beta distribution, and what you come to the conclusion is that the posterior also follows the beta distribution, but with some different parameters that it has. So this is about the Bayesian estimation part. Any doubt so far?
Ma'am,
Yes, Kiran, tell me.
what about this method of moments? Isn't it a good?
You don't know. Okay, method of moment, like method of moment is not very popular. I mean, MLE and Bayesian is something which is used quite like a lot. I mean, if you, I mean, you have already seen, no, not yet. I think once you move forward to different weeks, you will see a lot of places you are using MLE and Bayesian. Okay. You don't have to worry about method of moments. We'll just stick to these two methods, which is MLE and Bayesian. These two are good. Yes, Kaushik.
So, ma'am, in this, like posterior is proportional to likelihood multiplied by prior. In this, prior and posterior will have different distribution.
Okay. You're asking whether prior will be different than posterior?
Yes, ma'am.
Distribution, right? So yeah, I mean, it is not always true that your prior, I mean, the distribution, the prior distribution that you have taken is going to be also the posterior distribution. It does not always happen. In fact, even if you start with theta to be Bernoulli, okay, I don't think you will get the posterior to be also Bernoulli. You can try this exercise.
Yes, ma'am. If we take Bernoulli as a prior, then it will get beta is posterior.
Yes. So it's not that it always happens, but in the cases that it happens, where the prior you have chosen is the same distribution as the posterior, it comes out to be the same as prior. Then such kind of priors are given special name, and they are called the conjugate priors.
Ma'am, like this happens in with the gamma distribution, I think.
This happens with gamma. I think if your samples are coming from maybe geometric or exponential, then gamma distribution acts as a conjugate. If I'm not wrong, I may not be correct, but this is what I remember. So if your samples are coming from exponential or geometric, you use a gamma prior. I think you get a conjugate as gamma as well.
Yes.
Okay.
Yes, ma'am. Got it. Thank you.
Okay. So this was about the Bayesian estimation. All right. So, like for example, like we did this exercise of finding the likelihood estimator, like likelihood estimate MLE for P. Same thing we can extend, and maybe now if I'm saying that my data is x1, x2, so on till xn, if they are coming from Bernoulli P, but this time I have to use the Bayesian estimation. Maybe let's say my P follows a beta prior. Okay. So beta with, let's say, some parameter A and some different parameter B. Now I know that if P follows a beta prior, if it's a beta distribution, then this is going to look like x to the power alpha minus 1 minus x to the power beta minus 1. Right? So this is how it is going to look like. Now, if I have to see like whether my belief that I had for this P, is this the same, or whether once I observe the sample, it's going to be something different, right? So we need to see how does it change, or how different it is as what I have assumed. So if I have to find posterior, which is probability of P, given the samples, right? So I know this is proportional to the likelihood times prior. Sorry. So proportional to likelihood times the prior. Now my likelihood is what? Likelihood is probability of the samples, right? So probability of x1, x2, so on to xn, given your parameter P. Let's call it theta, just to not be confused with P. So theta, and the prior follows a beta distribution. So this is also your theta now. This is also your theta now. And this is also your theta now. This is also theta now. Alright. So I changed all the P with theta. Now, okay. So what is known to us, that this prior distribution is the prior for my theta is beta distribution. So now I'm saying that my theta follows a beta distribution with parameter a comma b. Then its PDF, its density function will be given by theta to the power alpha minus 1 and 1 minus 0 to the power beta minus 1, right? So instead of writing x, now my random variable is theta. So I'm just going to write theta to the power alpha minus 1, 1 minus theta to the power beta minus 1, right? And what is going to be the likelihood? The likelihood is going to be, the samples are coming from a Bernoulli distribution. So my likelihood is going to be product of this p to the power, sorry, theta to the power xi, 1 minus theta to the power 1 minus xi, where I is varying from 1 to n, and you have theta to the power alpha minus 1, 1 minus 10 to the power beta minus 1. Okay. So what is this going to be? So you have, again, you can take the log and work for it. So what will you get? You get theta to the power x1, x2, so on till xn. So you'll get, okay, so you have theta to the power x1, theta to the power x2, so on to the power xn. Okay. And then you have 1 minus theta to the power 1 minus x1, 1 minus to the power 1 minus xn. And then theta to the power this term remains. Okay. So what can you write this as?
Theta power sigma xi.
Theta to the power
Sigma xi.
sigma xi, right? I varying from 1 to n. And you can write 1 minus theta to the power n
N
minus
minus sigma xi.
over xi. I is varying from 1 to n. And then you have theta to the power alpha minus 1, 1 minus theta to the power beta minus 1. And this is going to be theta to the power sum over xi, I varying from 1 to n, plus alpha minus 1, 1 minus theta to the power n minus sum over xi plus beta minus 1. Okay. So now again, what I see is that my posterior again looks like a beta distribution. All right. It still has the form of x to the power alpha minus 1, 1 minus x to the power beta minus 1. Right. So remember that theta is now my x, right? Theta is a random variable. So this is of the form theta to the power sum alpha dash minus 1, 1 minus theta to the power sum beta dash minus 1. So I can write this posterior to be again a beta distribution with parameter alpha dash and beta dash, right? And what is going to be the alpha dash here? Alpha dash is going to be sum over xi plus alpha. And alpha is the parameter of your prior distribution. And what is going to the beta dash? Beta dash is going to be n minus sum over xi plus beta. Okay. So again, so we could prove that the prior is what we assume to be beta, and my positive also turns out to be beta, but with some different set of parameters. That's all. Any doubt so far? Okay. All right. So what we got is that probability of theta given my samples, it follows a beta distribution with some parameter alpha dash and some parameter beta dash. Now, just knowing the distribution, I mean, all we are saying is that my posterior now follows a beta distribution, right? But what is, I mean, like as someone had mentioned in the starting, like one very common guess that we can do if given a distribution is that we can find the expectation, right? So the same thing we can do here. So what we're saying is that now we know that, okay, my this parameter that we have theta is following a beta distribution with parameter alpha dash and beta dash. Then one possible guess that we can make for our parameter theta is that it could be the expected value of my beta distribution with these parameters. Okay, so I can find the expectation of let's call it, okay, so expectation of beta alpha dash beta dash, and whatever expectation you get for alpha dash beta dash, that is going to be an estimate for your beta. Okay, so that is going to be your Bayesian estimate for beta. Any doubt? Any doubt in estimation? We're moving to another topic afterwards. So if you have any doubt till here, you can let me know. We have not done anything new. I hope many of you are already aware of these topics.
Ma'am, is it the posterior we get always intuitional?
What
Like,
posterior is intuitional?
Hmm.
What do you mean posterior is always intuitional?
Like, we can reason it, no, but based on the priors. Like, we can understand what's happening.
No, I did not understand what you're trying to say. So see, the intuition part is in the prior, right? I mean, you are saying maybe this is what the distribution of my parameter can look like. So if that's the case, and I'm starting that belief, and now once I have the data, how is my belief varying? So now I know what is the distribution that my parameter is following, given that I have seen the data, given that I have observed the data. So once I know the distribution, I can find the estimate for my parameter. And for that,
Like,
expectation.
ma'am, if we take Bernoulli samples, then like from MLE we get the
For MLE, we get
like
sample
sample. Yeah, we get sample mean, right? So that is okay. So that is intuitional. Without doing that also we can just see that it makes sense. So that's,
right,
like
right.
that, like that. I mean, that's what I mean by intuition.
Okay. Arnav, you have any doubt?
Yes, ma'am. Can you please give a quick overview of this derivation done just now?
Okay. See. I'll tell you what I have done. So the very first thing is I have these samples. Okay. So I have x1, x2, so on till xn. And I'm saying these samples are IID, Bernoulli peak. But now the point to remember is that we are using the Bayesian estimation. So we have to assume that my P is a random variable. Okay. So if P is a random variable, I know P should have some distribution. So let's say my P follows P theta. Sorry. Or let's call it theta. Okay. It's much easier. So Bernoulli theta. So theta, we are saying it's a random variable. And if it's a random variable, it should follow a distribution. So I'm saying it has a distribution f of theta or p of theta. Okay, and this is my prior distribution. So this is my prior belief about the parameter theta. Now, once I have this prior belief about my parameter theta, then what we need to know is the posterior, and posterior is nothing but probability of theta, given that I have observed the samples. Right? So I know that posterior is proportional to the likelihood times prior. Now, what is the prior? Prior means prior knowledge about my parameter. And what I know is that my prior, my theta follows a prior distribution P of theta. Okay. So in our example, my P of theta was a beta distribution with the parameter AB. Right? And what is the likelihood? The likelihood you find for the samples. And the samples are coming from Bernoulli theta. Okay. So now you have, this is coming from Bernoulli theta. So now you write there probabilities. So what is going to be the likelihood? The likelihood is going to be theta to the power xi 1 minus theta to the power 1 minus xi. I is varying from 1 to n. And what is going to be the prior? The prior follows a beta distribution. So with parameter AB, so I can say that it is theta to the power a minus 1, 1 minus theta to the power b minus 1. Right? So I have to solve this part. And what we got is that my posterior again follows a beta distribution with some parameter alpha dash and some parameter beta dash. That's all. Is it clear?
Thank you. Yes, ma'am, please.
Okay. All right. Should we move to the next part? All right. So the next topics that we are going to start. So it is going to build up on what we have learned. So whatever estimation we have learned, the MLE, the Bayesian, this is what we are going to use. Okay. So now we are going to look at GMM, so Gaussian mixture model. So in GMM, if let's say if my data set is very, if it looks something like, if a data set is taking real values and it's more like in cluster forms, like at one place it's concentrated and then you don't see anything, then another place it's concentrated and don't see anything, something like that, right? So as in the lecture it's done that maybe I see a data set like this, maybe this is how my data set is looking like. So you see that it's, I cannot say that, this is on real line, that there is just one group of data in this, right? So I can see there are three kind of distributions from which it can come from. So in, here, okay, we'll come to that. So I cannot say that just because my data set, all these xi's are coming from R, one very obvious choice would be to say that, okay, maybe this data set is coming from a normal distribution with some mean mu and some variance sigma squared, right? Because we saw from a normal, we saw many real values. So just on the basis of that, we cannot say that this is, my data set is coming from a normal distribution with mean mu and variance sigma squared. So what we are doing is, whatever data set we have, let's visualize it, and we're seeing these three clusters that it has, right? So what we can assume is that instead of saying that it's coming from one distribution, which is normal with some mean mu and some variance sigma square, this may not be a very good idea to do it, right? I mean, it's a very poor distribution to guess, right? Because since we have observed these samples, and if I look at this point, then I will say that it has a very low chance of coming from a distribution, while there's a very high chance of coming from this distribution. So instead of that, what we can do is we can fit three normal distributions on this, right? So we can have something like, I mean, wherever you see the data set, you can have a peak, and then it goes down, and again here you have a peak, again it slows down, again here you can see a peak, right? So maybe this is a better idea, right? So something like this is what we can expect. So what we're saying is that now my data set is not coming from a single normal distribution with mean mu and variance sigma square. Now instead it's coming from three separate normal distributions. So I'm saying it is coming, I have a normal distribution with mean mu1 and variance sigma 1 square, normal with mean mu2 and variance sigma 2 square, and normal with mean mu3 and variance sigma 3 square. Okay, so now we want to see how to estimate the parameters when you have a setting like this. I mean, when it's not coming from one distribution, but a mixture of three normal distribution, or it can be not just, I mean, we cannot restrict it to maybe it is mixture of 2 Gaussian, mixture of 3 Gaussian, mixture of 4 Gaussian, it can be anything, and can be anything. So it can come from any number of mixture of normal. So if that's the case, the number of parameters that we have to estimate now has increased a lot, right? Initially, if I'm saying that my x1, x2, so on till xn, if they are coming only from one distribution, which is normal with mean and variance sigma square, and if I have to, I don't know what are these parameters, and I need to estimate these parameters, I can use the MLE, and I can find my mu hat ml, and I can find my sigma hat ml, right? It's not very difficult, and it's only two parameters that we have to estimate. But now look at this case when we are saying that my samples are coming from these three, mixture of these three Gaussian distribution. So now the parameters that we have to estimate, we are going to have to estimate is, there is this mu1, there is this mu2, there is this mu3. Then there is a sigma 1 square, there is a sigma 2 square, there is a sigma 3 square, right? But not just this. I mean, it doesn't stop here. I mean, these are the 6 parameters that we have to estimate. So what, I mean, you have to generate a data set in such a way. So we'll have to assign some probability to it. So if I call this mixture 1, call this mixture 2, and we call this mixture 3, then in order to generate this, I will have something like, there is this probability that my Zi, I will tell you what Zi is. So Zi is 1 is going to be pi 1. Probability that my Zi is equal to 2 is your pi 2. And probability that my Zi is equal to 3 is pi 3. So this is something that we are doing here. And what are these Zi's? So if, let's say, if I'm saying this is my x1, this is my x2, this is my x3, this is my x4, x5, x6, x7, 8, 9, 10. Okay. So corresponding to this x1, I will have a Z1, right? So it's just like the cluster indicators that we have seen in clustering problem. So I'm saying for x1, there is Z1, for x2, there is Z2, for x3, there is Z3, for x4, there is Z4, Z5, Z6, Z7, 8, 9, 10, right? So for each of these xi, so for each of these xi, you have a corresponding Zi. But now these Zi's can only belong to either 1 or 2 or 3. Okay. So what we are saying is, let's say the probability that my x1, if maybe z any xi, so probability that my zi is 1. I mean, my cluster indicator or my group indicator or mixture indicator, anything what you want to call. So let's take the mixture because we're talking about the mixture distribution. So probability that my zi is coming from mixture 1 is p1. Probability that zi is 2 is pi 2, and probability that zi is 3 is pi 3. So these are, I mean, these are the three these three other parameters are something also there that we have to take care of, right? We need to know what are these estimates, what are the estimates for this pi 1, pi 2, pi 3. And not just that, I mean, there is a relationship between pi 1, pi 2, and pi 3. What is that? Since these are the probabilities, we all know that probability should always lie between 0 and 1. And the sum of all these pi i's should be equal to 1. Right? So this is constrained on this pi i's. I mean, this is something that it should hold. So what are the additional parameters that gets added? Additional parameter that gets added that you need to estimate is pi 1, pi 2, and pi 3 now, right? But since these are probabilities and sum of pi i's has to be 1, I need only 2 parameters. I need to know only 2 parameters from here, which I should estimate. From here, you need to 3 parameters, 3 parameters, and 2 parameters. So in total, now I need these 8 parameters to be estimated. Okay. So what are the ways we know we can estimate the parameters? The very first thing what did we learn is to do the MLE. So if we do MLE, let's try to see what happens when we do MLE here. So okay, so what do we have? We have 3 distributions, right? A mixture of 3 distribution. I'm saying I have normal with mean mu1, sigma 1 square. I have normal with mean mu2, sigma 2 square, and I have normal with mean mu3 and sigma 3 square. All right. So these are the parameters that we have. These are the 3 distributions that we have. So what are the set of parameters? What are the set of parameters? Let's call it theta. And the set of parameters that we have is mu1, mu2, mu3, sigma 1 square, sigma 2 square, and sigma 3 square. And then there is pi 1, there is pi 2, and there is pi 3. I need to estimate all these. So if I use the likelihood, MLE, so what will happen? I will do likelihood of theta, and theta is set of all these parameters. Given that I have observed these samples x1 to xn. Okay. So how do you find the likelihood? We just take the product of the distributions that my xi follows. So let's say my xi follows a distribution f. I is range from 1 to n, and this is a mixture distribution, and we call it f mix. And it has a set of parameters. So xi, and we have theta. Yes, I see. Yes, Kiran.
Now what is this pi 1, pi 2, pi 3?
So pi 1, yeah. So pi 1 is the probability that my zeta is 1. Pi 2 is the probability that zeta is 2. Pi 3 is the probability that my zeta is 3. Any for any I, basically.
Okay.
I mean, see, if you have this samples, and I'm saying it is coming from mixture of 3 Gaussian, then there is, with some probability, my data set is getting generated from a certain distribution, right? And that is exactly what my pi is captured here.
Okay.
Okay. So these are just the probabilities. Now, so we need to find this. We need to find this. Okay. So how does the mixture distribution? How do you write the mixture distribution? So in this case, since it's a mixture of three Gaussian, this is going to be my f1, not f1. So pi1 times my f1 of xi given mu1 comma sigma 1 square plus pi2 times f2 of xi mu2 comma sigma 2 square plus pi3 times f3 of xi with mu3 comma sigma 3 square. Now all these FIs are nothing but a normal distribution, right? So in short, I can write this whole thing as product of, and then I need to take the, first I need to add, right? So I will just write pi, maybe pi j fj of xi with mu j sigma j square, and j is varying from 1 to 3, right? Because this indicates a clusters. This indicates the number of mixtures, and number of mixtures that we have is 3. So this is what it is. Now I is varying from 1 to n. So this is what my mixture distribution PDF looks like. The mixture of 3 Gaussian, if you have to write, this is what it looks like. Now what you can do is, instead of this part fj, you can just put your whatever the PDF of normal is, that is 1 upon sigma j under the 2 pi e to the power minus 1 upon 2 pi xi minus mu j divided by sigma j square. Right? That's all. So this is what we are trying to solve now. All right. So if yeah, so let's come back to this. So what we have L of theta, which is likelihood function. This is coming out to be product of I varying from 1 to n, sum over pi j fj xi mu j sigma j square, where j is varying from 1 to 3. All right. So instead of this part, I can write my distribution, right? So once you write the distribution here, which is going to be j varying from 1 to 3, pi j 1 upon sigma j under root 2 pi e to the power minus 1 upon 2 xi minus mu j divided by sigma j whole square, and this is the product. If you look at this expression of likelihood, do you think we should go for the log likelihood, or we should try to solve this? What do you think? Should we go for log likelihood or
log likelihood?
Log likelihood, right? Because it looks very complicated, and it's quite difficult to solve this. So what we can do is we can take the log likelihood. So we'll take log of L beta, and if you take the log, your product gets converted to the summation. So it becomes I varying from 1 to n log of all this. What you have here, we'll just put in this. This is what you get. Now, even if you take the log, still it's quite difficult to solve, right? Because see, now you have inside it, you have pi j varying from 1 to 3, 1 upon sigma j under 2 pi e to the power. So this e to the power, even if it comes, this term will go. I mean, you still have this part and this. I mean, again, it's very complicated basically. So even if you take the log, right, it's not very easy to come to a explicit solution for theta. I mean, the way we were able to write for like in case of Bernoulli distribution, we were able to get a very nice way to write my theta. Here it's quite difficult, like because why is that? Because see, we need my mu1, I need to write for mu2, I need to write for mu3, and pi1, pi2, pi3, sigma1, sigma2, sigma3. So if we try to solve this, it's still not going to help us. Okay, so finding, I mean, going through this MLE part is not helping us in finding out the estimates for this parameter. So what we will do is so now if there are no if it's not possible to do it analytically using the ML estimation, then again, of course, there are optimization techniques which we can use to get these to get a decent values of these parameters. I mean, I can maybe use gradient descent algorithm or stochastic descent algorithm or some other Newton, some other different technique. Okay, we can use any of those and we can come to maybe those will do also a decent job in finding out a good estimate for these parameters. But here we are not moving. I mean, we are not doing the optimization here. So what we'll instead do is, I mean, we'll not take those very decent route and all. What we will instead do is we will see how the EM algorithm can help us in finding the estimate for our parameters. So what is going to be mu j hat, what is going to be sigma j hat, and what is going to be pi j hat. These can be computed using the EM algorithm as well. So we'll see how this EM algorithm works. So this EM algorithm, right, this works quite well in case of missing data. So just like in this example, where what we know is that I have these samples. I have this x1, I have this x2, so on to xn. And what we're saying is that it is coming from a mixture distribution. But what is something that we don't know? We don't know what is my z1. We don't know what is exactly is my z2. We don't know what exactly is my zn. I mean, we don't know these things. I mean, we don't have the complete information basically. All we are saying is that my samples are coming from mixture distribution, but what exactly, I mean, which data point is coming from which mixture, that information we don't have, right? So that is something that is unobserved. So whenever you come across a situation like this where you don't have the complete knowledge about your data set, EM algorithm works quite well, or maybe some missing data cases or something like this, what we have just seen. If you have situations like this, EM algorithm works well. So now, how do we use this EM algorithm to find these estimates for these parameters? So we'll introduce another term to it, and okay, before I move forward, I'll just any doubt any of you has? We'll move. Are you able to understand this? Yes. Okay. What about others? Is it okay? All right. Okay, it's good. Okay. So let's see how the CM algorithm works. So now, see, we have. Let's write this likelihood again. So we had this log of L theta, and this log of L theta was sum of log of, so I going from 1 to n. We had sum over j varying from 1 to let's take k in general for k number of mixture. We are going to have pi k e to the power minus 1 upon 2 xi minus mu k, sorry, it's mu j, right? Mu j divided by sigma j whole square divided by sigma j under root 2 pi, right? This is what we have. So what we will do is we will introduce another parameter. So we already had these set of parameters. I mean, we had these mu j's, we had this sigma j, and we had this pi j. Now what we're saying is let's introduce more set of parameters. And these parameters are basically the probabilities, again, is what we're adding. So we are adding these parameters lambda I of j. I'll tell you what these lambda I of j are. So see, you have the data set x1, x2, so on till xn. Right? This is my data set. Now we have three mixtures. I have, or in general, I'm talking about k mixtures. So we have k mixtures. So what is the probability that my data point 1 is coming from the mixture 1? Okay. So that probability is, I will give by lambda 1, 1. So here 1 denotes the data point, and here 1 subscript denote which in which mixture. Okay. So next would be lambda 1, 2, right? And so on, you will have till k. So lambda 1, k. So each of these pi i's denote, like, so this will say what is the probability that my data point x1 belongs to mixture 1. Okay. This will say what is the probability that my data set data point x1 belongs to mixture 2. So all these probabilities these probabilities is something that we are introducing from our side. So now see, there again has to be some constraint. No? I mean, if you have these three mixture, let's say, and I'm saying if this is my point x1, then probability that it can come from mixture 1 or mixture 2 or mixture 3, they all should add up to 1, right? So if this is my normal distribution 1, this is the second distribution, this is my third distribution. So this cannot just come from this. I mean, though I can easily see from here that my x1 is has a very high probability of coming from mixture 1, but we cannot discard the fact that this x1 still has the probability of coming from mixture 2 as well as from mixture 3. Even though this probability is very less, it is very less, but still there is a chance that this x1 can come from these distribution, not from the first one, right? So that is why these probabilities are there. Okay. Now, if I'm saying these are the probabilities, then definitely all these should add up to 1. So what I will say is that sum over lambda j, where j is varying from 1 to k of 1 should be equal to 1. Right. Similarly, for x2, you will have some probabilities. So you will have lambda 1, so lambda 2 of 1. You will have lambda 2 of 2. You will have lambda 2 of k. Okay. And then you will have lambda n of 1, so on till lambda n of k. So you have all these probabilities with you. So in this formulation of the log likelihood, what we are going to do is we are going to multiply and divide by this term. So we are multiplying my numerator by lambda lambda I, so I is for data point, and j. Okay, so we're multiplying by this and we're also dividing by this. So let's put the division here. That's right. So this is what we're doing. Now, if we're doing this, what we will get is, let's try this. So this is going to be, now you have summation I varying from 1 to n, j varying from 1 to k. You have lambda ji, log of all this term. So you have pi j e to the power minus 1 upon 2 xi minus mu j upon sigma j whole square times 1 upon sigma j under root 2 pi, and I will divide it by pi ij. Okay, this is what we are introducing. Okay, there's no, we have done nothing. We just we just added this lambda term in both numerator and denominator. Now, once we have this, this is what we are calling it as modified log likelihood. Okay, this is not the likelihood, but this is the modified log likelihood. So maybe I can call it as okay, let's write modified log likelihood. So using this, I don't know if you are familiar with the Jepson inequality, but what happens is that this log of theta that you had, okay, actually, it's a little older because we took the log inside, no? So there is this Jensen inequality, and because of that, we are able to write this. Okay, I mean, we are able to formulate in this way. We are saying that my likelihood is greater than this modified log likelihood. So this is basically kind of giving you a lower bound on the likelihood. Okay, so now instead of using my likelihood function, I will use my modified log likelihood, and we will find the all these parameters. So once we have a setup like this, where all these logs, once we get this, we can easily do. You can easily find your mu j, sigma j, and pi j. So any cases like what we can do here to find these parameters? I mean, if you look at this likelihood function, what do you think we should do to find these estimates? Here you're no longer dealing with one variable. I mean, it's not a optimization problem in one variable. Now you have multiple variables, right? So if you have to take the derivative, how do you deal with it? Anyone
So-
has? Yeah, tell me.
Differentiate with respect to one parameter and take other constant.
Yeah, right. So we'll differentiate with respect to one parameter and we'll keep the other parameters constant. So this is the trick that we will use to find these estimates. So there's a lot of math involved here. I mean, when you try to find out these mu and sigma and pi's, I'm not planning to do it, but if you are interested, you can take a look at it. I don't think even it's been done in the lecture completely. So what we'll do is we'll fix my lambda. So the very first thing is we'll fix my lambda and we will maximize over theta. Maximize over theta. And the second thing is that we fix our theta sorry, we fix our lambda, right? We fix lambda and maximize over eta, and second possibility is that we fix theta and maximize over lambda. So in the process of doing this, I mean, when you fix one term and maximize over other, and you try to find out the value. So this process is kind of like giving you these expectation and maximization part of the algorithm, what it says, right? So EM is basically this EM algorithm. Here E stands for expectation. So it's not very important right now, like why is it expectation? And M is this maximization. So there is some other very, I mean, there are certain proofs to see how this expectation is coming into picture. But since it has not been done in this course, we'll not go for that. So this EM says expectation maximization algorithm. Okay. So what this algorithm says is that we initialize our theta. Okay. So we initialize theta. So we'll call it theta naught. And when you're saying initialize theta naught, it means I want to initialize my mu1 naught, mu2 naught, so on till mu k naught, sigma 1 naught, so on till sigma k naught, and so the square. And then you have pi 1 naught, so on till pi k naught. We initialize this. Okay. Once you have initialized it, I am going to follow these two steps, E and M. So until convergence. So I'm saying until convergence. And when I say until convergence, it means that at any iteration t plus 1, if I reach a stage when my theta, let's say if this is my theta t, and if this is my theta t plus 1, okay. So if I reach to a stage where there is very, I mean, for any epsilon, for any tolerance that you set, and this tolerance are generally set quite low, like maybe 10 to the power minus 3, 10 to the power minus 5, and so on. So until you reach to a stage where my theta t plus 1, the difference between theta t plus 1 and theta t is quite small. Okay, so it's, I mean, you reach a stage when this difference is even less than the tolerance that you have set. So this tolerance is given by epsilon. So when you reach a stage when this quantity, when this term is less than epsilon, I will stop. I mean, until then, I will do the two steps. So one is the E step. So in the E step, what we are doing is we are trying to find the lambda t plus 1. Okay, we are calculating these probabilities. This is nothing but probabilities, right? So we're calculating lambda t plus 1, and this lambda t plus 1 is arg max of the modified log likelihood. I'm writing it as MLL of theta t comma lambda. And you want to maximize this. All right. So initially we already have set up these theta naught. So you will find the initial probabilities based on the thetas that you have set, initial theta that you have set. You will have theta, you will find these probabilities which are given by lambda t plus 1. So you will perform basically two steps. So once you have these lambdas, then you can fix your lambda and maximize your M, right? Maximize your thetas. So M step is nothing but maximizing or finding the parameters that gives the maximum likelihood, right? So then you will do theta t plus 1 to be arg max of theta of the modified log likelihood of lambda lambda t plus 1 comma theta. So these are the two steps. So until I reach this stage when there is when this difference becomes very low, very, very low between these two terms, then until then I will keep on doing this. I will keep on performing E step, M step, and I will have I will get my thetas, right? And like whatever thetas you get in, let's say, the previous step, t minus 1th step, you will store somewhere. Then you compute for the next iteration. Then you see the difference. And once this difference becomes significantly smaller, then you stop. Then you end the algorithm. Okay. So this is what happens. So while doing this process of E step and M step, what we get is that see, this M step is supposed to give you this theta's MLE, right? So what in this theta d plus 1, what we get is we get mu hat k of mml. Like theoretically, this is the value you get. Okay, I mean, this is the experiment that we are performing, but theoretically, when you do it, you get this mu hat to be equal to weighted. So you have lambda ji. Since we are looking for, or let's call it k, because we are looking for kth mixture. So lambda ki, where I is varying from 1 to n, xi divided by lambda ki, where I is varying from 1 to n. This is just the weighted mean is what you can think of, and these are the weights. Okay, so this is basically giving you the estimate for the mean of the kth mixture, right? And this is this turns out to be the weighted mean, and weights are given by lambda ki. The variance that we get, which is sigma k square hat of mml, is again the weighted sample variance. Like if you don't look at the mixture distribution, if you look at in general the normal distribution, then in that case I know if I have to find the estimate for mu, it's nothing but a sample mean. If I have to find the estimate for the variance, it's nothing but the sample variance. So in this case, where you have a mixture of normal or mixture of Gaussian to say, here the estimate of mu I'm getting to be a weighted mean, estimate of variance I'm getting to be a weighted sample variance. And how can you write this? This is going to be just, so the weights are given by lambda ki. Now, what are the random variables? This is xi minus mu hat k mml, this square, divided by, so I went from 1 to n, divided by all these weights. Okay. So this is the estimate for the variance, and the estimate for the pi i's that we get is, so pi k hat of mml turns out to be sum over lambda ki, where I is varying from 1 to n, divided by n. If you are interested in proving it, I mean, it's not difficult, but it's a little lengthy process. So you can try this. It's nothing much. See, this is the log likelihood, modified log likelihood that we had, right? And just take this, you fix your lambda, and you differentiate with respect to first. I mean, let's first try to do it for mu. So if you wanted to find it for mu, again, you'll have to treat other variables as a constant. So you'll have to treat your pi j's and sigma j to be constant in order to find mu j. You will do that, and you can find the mu hat j. Similarly, when you have to find it for sigma, you treat mu and pi to be constant and differentiate with respect to sigma. And same thing goes for the pi's, but there is a difference here, is that in pi, when you're trying to find pi hat j, I mean, now it is no longer an unconstrained problem. There is a constraint on pi, right? And what is the constraint? The constraint is that the sum of pi j's has to be 1, right? So now it becomes a constraint problem. So you can use a Lagrangian, and you can find your pi hat j. So doing all the maths, what we get is this is my mu hat k, this is my sigma hat k, and this is my pi hat k. So these are basically giving that if I have, let's say, mixture of 3 normal, okay? So if this is my mixture of 3 normal, so I am saying for any k, so in this case k is equal to 2, this is the estimate of the mean that I get. This is the estimate of the variance that I get, and this is the estimate of pi's that I get. Okay. These are this is what these quantities are. And now there is this another term that we are introduced, what is what we're finding in the E step, which is the probabilities, right? So these probabilities were given by these lambda ki, right? And what are these lambda ki's? They are the probability that given my data point xi, right, what is the probability that my zi is equal to k? This is exactly what this term is. And if you use the Bayes theorem, you can write this as probability of xi given zi is equal to k, times probability that zi is equal to k divided by probability of xi. And I know probability of zi is equal to k is nothing but pi k. So my lambda ki is probability of xi given zi is equal to k times pi k divided by probability of xi, right? And while you try to prove this, try to do the derivation, you will get a form like this. So again, it's I cannot just write the expression. You can try this, but this is what you have, and the estimate that you get is something of this form. The estimate that you will get while doing the derivation will look something like this, okay? Where you will get a probability, where you will get this probability as well. Okay, I know there are a lot of things going on, but are you able to follow this?
Madam, I have a doubt.
Yes, tell me.
Yeah, can you hear me, madam?
What can I?
Am I audible?
Yeah, you're audible.
Yeah, in the last derivation, lambda ki, in this, the denominator you have written like p of xi.
Correct.
Yeah, that is total law of probability, right?
This is Bayes theorem, no?
Yes, madam. But p of xi can come from any cluster, right?
But yeah, then it will be a sum of all these things basically. Probability of xi given zi is equal to k times probability zi is equal to k. You do the summation. You're asking this, no? That probability of xi should be sum over probability of xi given zi is equal to j given probability of zi is equal to k. J is varying from 1 to k, right?
Yes.
Yeah, this is what you will write. Okay.
Yeah.
I have not done the proof because it's quite big. Okay. So again, you are free to go ahead and try to do these proofs. Not very difficult, I say, but it's a little
Is it a lecture?
I don't think it's available completely in the lecture. It's not completely available, I guess. I remember. You can, but you can try. You can try doing it yourself.
Like the book that is recommended, no? PRML.
PRML.
Can you refer to it for the derivation?
It should be there, maybe. PRML, it should be there.
Okay.
But I would say don't take the reference. First try it yourself. Then you have, if you're not able to understand, of course, you will find some resources where these things are easily available. So once you, the thing is that once you know how to derive such things, you don't have to remember these terms. You don't have to remember what is the estimate in this case. What is the estimate of in this case? So you'll get some practice. Okay. So this is about the EM algorithm, and I mean, we are trying to like, in case where we don't have the complete information about my data set, we can use the EM algorithm to get the solution, to get the estimate, to find the estimate of the problem. So like, as in case of the clustering, like when we are doing the k-means clustering, there it was more like hard clustering, right? I mean, once you run this Lloyd algorithm, we are saying that, okay, this point goes to this cluster, this point goes to this cluster, and so on. But here, this is not the case. It's more like doing a software clustering, where you are assigning a probability of probability for each of the point to be in a particular cluster. So this is something called a soft clustering. Okay, and it will converge to some. When you run this algorithm, it will converge to some local maxima.
Ma'am, what clustering?
Sorry. What is it?
What clustering you are saying?
No, I'm saying this problem is more like a clustering problem, right? What we just did.
Okay.
So this is more like doing a soft clustering, where we are assigning some probabilities. We are assigning probabilities to each of the point to be in a particular mixture. But in k-means clustering, we were doing a hard clustering, where after we run the algorithm, we know that, okay, this point is in this point is in this, and so on. So this also converges to a local, some local maxima, just like my k-means. But EM is mostly useful. I mean, you should go for EM algorithms in all the situations where you don't have much information about your data set, you don't have the complete knowledge about your data set, or if you have some kind of missing data, then in such scenarios, EM algorithm is quite, it works quite well. Okay. So, okay, I think we still have some time, so I can show you maybe just one part of finding maybe mu, and then you can try to do it for maybe sigma and pi. Okay, so I will show you how did we reach to this mu. So, see, what we had was, we wanted to, so very first thing, you fix your lambda, and we want to maximize over theta. Okay, so we want to maximize over theta, and what is the modified log likelihood? It is I varying from 1 to n, sum of j varying from 1 to k, lambda j I. Then you had log of this whole thing, which is pi j to the power minus 1 upon 2, xi minus mu j upon sigma j whole square divided by sigma j into 2 pi, right? And then we have to also include this lambda ji term here. Okay, so we have this, and okay, so we are saying fix your lambda. Okay, so fixing your lambda means I will fix maybe for k I'm fixing, and if we have to maximize over theta, and if we are trying to find maybe first mu hat, then I will keep my pi and sigma to be constant, and we will differentiate with respect to my mu. So in that case, it will become, so you have informations. I'm fixing my this, so maybe for j I'm fixing, and you have sorry, so you're fixing, we don't have this double, no, it's fine. So this is fine, and you have log of this. So you can just separate this. You can write this whole thing as log of pi j. Then what other term do you have? You have this second term, which is see, log, if it goes here, it becomes, you only have this term left. No, so it is minus 1/2 xi minus mu j whole square divided by sigma j. Is okay. So this is the term you get. Then you have this denominator term, this whole thing. So this is going to be again minus of lambda ji, and we will do since it's a log and this is just a constant, log of sigma j under 2 pi. Okay. And outside we have this. Now you differentiate with respect to mu. So I know this term does not have mu, so this will this we can ignore. This term doesn't have mu, we can ignore. So the only term left is to differentiate this. And what is this going to be? This is going to be minus 1/2, 2 times xi minus mu j divided by sigma j. Right? If this gets cancelled out, and since it's minus, this comes plus. Okay. So okay. So this is what we have. Now let's write this. So you have I varying from 1 to n. Then you have this lambda ji, and you have this xi minus mu j with you divided by sigma j square. Oh, sorry, square of the sigma j square will be 10. This is what you will get. Now you put it to 0. What will you get? You will have sigma j 1 or okay, what you were following? You were following mu j to be 1. Okay, the way of text, and I is varying from 1 to 1. Okay. So this is just 0. It force that from 0 and sum over lambda ji xi minus sum over lambda ji j varying from 1 to 10, from 1 to 10. Substitute the 0 and what do you get? You get mu j hat to be this term, which is sum over lambda ji xi. I is varying from 1 to n. Divided by sum over lambda ji, where I is varying from 1 to n. Because it's a constant, I mean, mu j does not depend on this. I mean, it doesn't have I term. I can just write it out. So this is how we can get the estimate for ML estimate for my modified log likelihood. Is it clear to all of you? No, yes. Any issue that you had during this? No, this is all fine. Were you able to follow what I did? Okay, all right. So yeah, so same way, I mean, now we saw how to do it for mu. Now if you have to do it for sigma, you keep your mu and pi constant and differentiate with respect to sigma. You will get your ML estimate. Same thing you will do for pi. It just might become a constraint problem. Okay. Yeah, so that was all we had in week 4. Anything else? Any doubt?
Thank you, ma'am.
Okay, all right. If there is nothing, we can close. But yeah, we'll see. Okay, I think we'll see for the session timing that you have raised for Monday. We'll see if it's possible, and we'll try to change, because yeah, like coming to the session without studying, it's not very beneficial. Will be beneficial for you as well. So we'll try to see if it can be moved and if it doesn't clash. All right. Anything? Any doubt in week 4? Okay, then if there is nothing, we can close. Thank you, everyone.
Ma'am,
Yes.
like for extra practice purpose, like to suggest any